Hello, I'm Grandin Gill. I'm a professor at the University of South Florida, and this is the first in a series of 5 lectures that looks at the impact of complexity on strategy and decision making. And in this particular lecture, we're going to try to clarify what is meant by complexity and how the different types of complexity interact with each other. We're going to cover a number of different topics in this lecture. First, we're going to focus on 3 distinct types of complexity, each of which behave in different ways. Then we're going to kind of zoom in on the concept of rugged landscapes, which relates to the 3rd type of complexity, and how that impacts the behavior of environments. And we'll introduce the notion of a complex environment. Finally, we'll look at the challenging trade-off between being efficient and being adaptable, which is very, very important when we're dealing with complexity. One of the challenges presented by complexity is that when any 2 people talk about complexity, chances are they're referring to something different. So in this first segment, what we're going to do is look at 3 distinct types of complexity, particularly complexity as it relates to performing a task. Philosopher Karl Popper introduced the concept of 3 worlds. The world as we experience it, the world as we represent it in symbols, and the real world. It turns out that these worlds are a good way of thinking about the different types of complexity. So we're going to look at complexity as it's experienced, complexity as it's related symbolically, and finally complexity of the real world and how the world reacts to what we do. Let's start by thinking about complexity as we experience it. To get a sense of what I'm talking about, let's conduct a simple thought experiment and ask the question, does driving a car seem complex? Now, driving a car is a different experience under different conditions. For example, when you're driving a car in very routine circumstances and there's light traffic and you've been driving for 20 years, it hardly seems complex at all. Indeed, you can go miles and miles without even recognizing that you're doing it. It requires very little mental effort. But think back to when you first started to learn how to drive. Somehow, at that point in time, things like holding the steering wheel, pressing the brakes, if you're old, operating a gear shift, seemed intensely challenging, and it was so hard to pay attention to all those things at the same time. What that suggests is that experienced complexity can change very much with respect to the context and kind of represents how much attention, how much mental effort it takes to actually perform the task. Even when we're an experienced driver, the experience of driving on an uncrowded highway that's straight for miles and miles is very different from driving in traffic during a snowstorm in the Northeast. So experienced complexity can depend very heavily on the task context. And over time, what we experience as being complex changes. There's a good reason that our experience of complexity changes over time. In fact, our brains are kind of wired that way. When we're repeatedly exposed to the same concept over and over again, we basically condense what we're doing into what are called chunks. It turns out that the human brain can handle some number of chunks, 5 to 7 is the number that's usually thrown out, at the same time within our working memory. What happens is that as we do something over and over again, those chunks get bigger and bigger. For example, there is one psychology student in the 1950s who trained himself to memorize a sequence of zeros and ones so that he could hear over 1,000 of these with one repetition and recite the whole pattern of numbers back. The way he did it was he imagined that these were related to heats in a running race, and he translated the zeros and ones into times, and the race got larger and larger as he developed this facility to work with the memory. And eventually he had a whole track meet, and he could actually translate those zeros and ones as they were coming in into this representation. And that process of chunking is critical in learning things like calculus. For example, you cannot learn algebra until you've learned to chunk basic facts like multiplication, so that you have enough working memory capacity to look at the equations. You can't learn calculus until you've got enough practice with algebra so that you can look at the new calculus concepts without having to think about the old algebra concepts. Now, the same thing happens with activities that are repeated over and over again. If you look at a skilled pianist, for example, there is no way the human brain could operate quickly enough to concentrate on each finger being pressed in a complex piece, like one by Rachmaninoff. But what happens is, by practicing over and over again, you essentially develop these automatic sequences, so you don't have to think about your hands moving. And in fact, a really experienced pianist performing a well-practiced piece can hold a conversation while still playing that piece, which would absolutely be beyond any of us who are learning to play the piano, which is an example of something that puts a lot of cognitive strain on us. The bottom line here is that as we repeat something, whether it be repetitive exposure to a concept or repetitive exposure to an activity, it reduces the need for attention, and that is the reason why experienced complexity goes down. Now, an interesting aspect of experienced complexity is the existence of a sort of cognitive sweet spot. If we do not have to pay enough attention to a task, we get really bored. On the other hand, if a task demands too much attention, we experience information overload. In either case, being bored or experiencing information overload, our performance declines. So what we like to do is we like to have tasks at this peak, sometimes referred to as the inverted U curve. And one of the things that we will do when performing tasks is try to tune the task so it fits this particular sweet spot of attention. And that becomes very important when we look at how we make decisions later on in the sequence of lectures. The bottom line of this is that experience complexity is largely driven by unfamiliarity. The less familiar the task, the more likely we are to experience it as being difficult, the more likely we are to experience uncertainty, and the more likely we are to experience ambiguity. How do we interpret the information that's coming in? For example, is this someone playing the saxophone, or is this an image of a young lady? So, just to state it over again, unfamiliarity is the driver of experienced complexity. Presenting this in a graphic way, experienced complexity goes down with repeated performance of the task. And we will return to this concept later on when we talk about something known as the learning curve. And these particular axes would normally be logarithmic, but it doesn't really matter. The key thing here is that the complexity goes down, because that is not true of all types of complexities, as we will see shortly. Our second type of complexity is what I call intrinsic complexity, and this is complexity in the world of symbols, or complexity in how we represent the tasks that we are performing. To illustrate the concept of intrinsic complexity with an example, let's take a look at these two maps, the map of Manhattan and the map of downtown Boston. Which of these two maps is more complex? Well, almost everyone, in looking at the two maps, will indicate that the map of Boston somehow seems more complex. But why is that? That's what we'll look at in this segment. Before we delve into the details, let's take a look at another example that illustrates the difference between experienced complexity and intrinsic complexity. Which task is more complex, the tasks performed by a new nurse or the tasks performed by an experienced doctor? Now, if we're dealing with experienced complexity, the previous type of complexity we talked about, the driver was unfamiliarity. So as soon as we know this is a new nurse, chances are he or she will experience greater complexity as a result of the unfamiliarity of the task than an experienced doctor would experience. On the other hand, if you ask most people the question, which of these activities are more complex, they would go with the experienced doctor. And that's because they're dealing with the intrinsic complexity of the task. So let's look at some of the different characteristics that produce intrinsic complexity. So what are some of the practical things that could suggest a high intrinsic complexity task? Well, one example would be the number of paths that the task could take in a given situation. We would, for example, expect that a doctor could handle a greater variety of symptoms and cases than a new nurse. That suggests that the job of the doctor is more intrinsically complex. Another example of this is the amount of time it takes to learn the task. There's no question that learning to be a nurse is very complex, but it can be accomplished with, say, a bachelor's degree or a master's degree, whereas learning to be a medical doctor requires 4 years of medical school, plus internships. It takes a lot longer to learn to be a doctor. Another indicator is the number of rules in the description of the task. And again, the doctors have to learn many, many different rules, symptoms related to diseases, what you can and can't do. Nurses also have to learn a lot of rules. It's just slightly fewer because when they reach a certain situation, they will always refer it to a doctor. Finally, there's a question of how compressible the task is, and that takes us back to the map of Boston and the map of Manhattan, because if you look at the map of Manhattan, it's laid out like a grid. Intuitively, you can get a sense that we could compress that map, and any set of directions we had to get from point A to point B, we could do by simply describing how many avenues to cross and how many streets to cross. Boston, on the other hand, is organized according to no rational principles. The legend is that the streets were laid out based upon the cow paths, and apparently the cows were eating fermented grains because they all go in very, very strange directions. And in Boston, the typical intersection has like 5 streets coming into it, and basically there are no rules. It's just a free-for-all. But the point is it will be much, much harder to compress that. And when you ask for directions in Boston, there are usually 3 possible outcomes. One is they will say, I don't know. 2, they will make up something that is impossible to follow. And 3, they'll point you in the general direction and say, well, why don't you drive that way, and then you can ask for directions later on. And the reason is not that they want to be unhelpful, though that may be the reason some of the time, but the reason is that it is so complicated to try to explain the directions that you simply can't do it, and as a result, they're not confident in their ability to give them. Now, one of the indicators that I mentioned for intrinsic complexity is the number of rules. And one of the things that we see with intrinsically complex tasks is that over time, the number of rules tends to get larger and larger. And one of the things that you will therefore see is that representing these tasks gets more and more complicated. Some good examples of very intrinsically complex tasks include the regulations that defined Obamacare, and this was just after a few years. This is page 2300 and something of the Dodd-Frank Act. And the Dodd-Frank Act didn't even provide the rules. What it simply did is it identified all the different rules that had to be created. Here is a picture of the purchase chart for SAP, the ERP software. This is another example of rules run amok. If the program is that complicated to purchase, it's really hard to imagine how complicated it will be to use. And so over time, what you tend to see is that the number of rules, the size of the task grows in terms of intrinsic complexity. Now, this provides a very, very interesting contrast to experienced complexity. If you can recall, for experienced complexity, as we repeatedly perform the task, the complexity that we experience tends to go down because of chunking and elements of the task becoming automatic. When we're talking about intrinsic complexity, however, how we represent the task, what typically happens is the number of rules, the size of the task actually increases, and so complexity rises with time. And that's why you don't want to confuse the two types of complexity, because they behave very, very differently. Now, every once in a while, someone has a tremendous insight, and we can actually lop off some of the complexity that we find in a task. For example, when the notion of economic order quantity was developed, all of a sudden we could simplify how we determined how much stock to hold in inventory. A lot of what we try to do in teaching rules within an MBA program is to identify rules of thumb that simplify otherwise intrinsically complex problems. But under normal circumstances, what will happen is the intrinsic complexity of a task will grow as we learn more about the task and as we gain more experience with different cases of the task. It's now time to turn to the third type of complexity, which I call extrinsic complexity, which essentially deals with complexity as it relates to the real world, particularly how the real world rewards and punishes the activities that we engage in, which is not always a very simple thing. To think about what we mean by extrinsic complexity, let's take a look at two examples. The first example is a multiple choice test. And in a multiple choice test, the world rewards the test taker based upon the number of right answers. And so if you look at the mapping between your responses and your final score, each particular answer has a certain weight, and to determine your final score, you add up the scores on each answer. Now, what that means is that for any given answer, there's going to be a right answer, which will add points, and a wrong answer. And as far as your total score is concerned, all other things being equal, you will always do better, for example, if you answer question 17 correctly versus answering question 17 incorrectly. Again, all other things being equal. What that means is that you can decompose your final score into a series of individual scores on each question. That's a very simple relationship. We call that a decomposable relationship. Now, let's think about another example, the relationship between the ingredients in a recipe and the overall fitness of the final product, which you might measure in terms of how much you like it or dislike it. Now, if we had a decomposable relationship here, we would be able to give a definitive answer to a question like, is garlic a good ingredient? But you can't really answer that question because in some dishes, adding garlic makes the dish much, much better. And in other dishes, adding garlic doesn't help at all. There's a restaurant in San Francisco called the Stinking Rose, and every dish they serve has garlic in it. I would say the appetizers and the entrees were very good. There's always a crowd trying to get into that restaurant. I'd go next door for desserts. I really don't think that the garlic adds a lot to the desserts. Now, the reason for this is in a highly complex environment, all the factors that determine the fitness of the outcome interact with each other, so you cannot look at them independently. You have to think of them in combination with each other. So, as I just mentioned, simple relationships between attributes and outcomes are called decomposable. Where you have complex relationships, such as that of the ingredients to recipes in a cookbook, we're going to call that rugged. And we'll refer to rugged landscapes as being those that are very complex, and decomposable landscapes as those that are very simple. Now, this is a challenging concept to grasp, so we're going to provide some examples now. So, looking at the definitions, decomposable landscapes are one where the various attributes that we're looking at contribute incrementally to fitness. And what that means is that when you make an incremental change, it's likely to have the same impact no matter what the values are of all the other attributes. Stated another way, it doesn't matter whether you've got question 4 wrong or right. Getting question 17 right versus getting it wrong will always have the same impact, incremental impact on your score, using the multiple choice test example. Now, in a rugged landscape, the elements interact with each other, and so when you make incremental changes, you can have a totally different level of impact in one context than another. So, for example, if you've got a lamb dish, adding garlic can add significantly to how tasty that dish is, whereas if you're making a flan, chances are adding garlic is not going to help you. And I think thinking in terms of recipes is a very, very good way to think about rugged landscapes, because if you think of a cookbook, what it really is a collection of local peaks where each recipe represents the author's view of the best combination for making that particular dish. Because if the author thought that adding a little extra garlic would make the dish better, the author would have changed the recipe to incorporate that fact. If we wanted to represent this sort of graphically, in a decomposable landscape like the one on the left, if you've got 6 variables that contribute to overall fitness, each one of them operates within its own separate domain. And so different values of X3 will add fitness somewhere in this range. In a decomposable landscape, you really can't say that. You have all these variables, but because they interact, even relatively small changes in one variable can have a big impact on overall fitness. Going back to the recipe example, think about baking a cake. One thing people don't really give a lot of thought to is the baking powder, because I've never at least heard a chef say, oh, my cake is best because it uses the best baking powder. Yet, nonetheless, if you leave the baking powder out, that little half teaspoon of baking powder, you'll end up baking construction material instead of a cake because it won't rise. And that is a clear example of an interaction effect, because if you were to add, say, a half a teaspoon of baking powder to, say, a vindaloo curry recipe, I doubt that anyone would even notice. It might bubble a little bit more, but it would be an effect that would be pretty much invisible. So actions you take in some contexts, even little actions, can have a really large effect, whereas in other contexts they will have a small effect, or in some cases the opposite effect of what you would expect. For example, adding garlic to a lamb dish increases its fitness. Adding garlic to most of your dessert category reduces its fitness. Just to review what I just said, when we're talking about extrinsic complexity, what we're really asking is the question, what should we be striving for? And the term that I've been using is fitness. And the analogy for extrinsic complexity is a cookbook where each recipe represents a local fitness peak, because any incremental change to the recipe would make the recipe less good, at least in the author's opinion. And before you start cooking, you need to know what you're going to produce. Different contexts will have different fitness. Now, the greater the ruggedness of the landscape, which is the greater the extrinsic complexity, the greater the number of local peaks that you will have, and the sharper those peaks will be, so that even tiny changes can have a huge impact on fitness. And one of the challenges we face is that the number of combinations goes up dramatically. Just as a simple example, if you had a perfectly decomposable landscape consisting of 20 variables which were either yes or no, say a 20-question true or false test, basically in 20 investigations, you could figure out the optimum response, which would be the correct answer for each question. And you could experiment with each question independently. If you had the same 20 yes-no variables with a highly complex, a maximally complex landscape, there would be 2 to the 20th power combinations, which is just over 1 million combinations, and you would have to explore each one of them to find the global maximum. But on the other hand, there would be a large number of local peaks. The actual number is something like 50,000 local peaks that you would have to investigate. But to actually find the maximum fitness across the whole landscape, you would have to look at every single possible combination. The way I like to think of this is graphically, whereas in a decomposable landscape, every step you take in the right direction moves you closer to the one peak, because in a multiple choice test, using our example, the peak is every answer is correct, which is 100%. And as soon as you've discovered that one of your question responses is correct, then you've moved a step closer to that peak. Rugged landscape, there is no real concept of a right direction, because there are lots and lots of local peaks, lots of sharp drop-offs between them. And as a consequence, you really need to think about how you're going to explore this landscape. And you're much less likely to worry about finding the sharpest peak than finding a decent peak and trying to hold on to it as the landscape changes. Did I just say continuously changing? Well, one of the things about rugged landscapes is that, for the most part, they are not static. Uh, a rugged landscape is typically produced when you have many elements that are interacting with each other. The problem is most landscapes are not completely isolated, and as a consequence, they're linked in a certain number of values with other landscapes. So, for example, in evolutionary biology, where this concept came from, you can have two species that potentially interact with each other. For example, you could have a population of deer and a population of wolves. And if the deer population rises, that impacts the fitness landscape for wolves. If the wolf population rises, that impacts the fitness landscape for deer. And then you've got the climate, which some years will produce lots of vegetation, some years will produce less vegetation. So the fitness landscape and the local peaks are continuously changing. The more rugged the landscape, the more significant those changes will be, because as the ruggedness of the landscape grows, incremental changes can have a larger and larger impact on fitness. So all of this leads us to a broader question, which is, what are the characteristic behaviors of extrinsically complex environments? This question leads us into an interdisciplinary area of study known as complex adaptive systems. And one of the behaviors that is characteristic in these systems is that behavior is not random, but it is completely unpredictable. And the characteristic behavior is one that's sometimes referred to as punctuated equilibrium, which is to say the system will enter a period of orderly behavior for a while, and then suddenly that behavior will change. And sometimes after the change, it will go back to the old orderly behavior, and sometimes it will exhibit an entirely different pattern of behavior. So whereas continuous change would look, kind of like a random pattern about this sort of general trend line, in punctuated equilibrium, it is much, much harder to predict the nature of behavior, and the ways of optimizing an organization's fit with the environment during periods of equilibrium is often very different from the way the organization has to optimize its behavior in periods where you've got these punctuations or these discontinuities. And we'll talk about that a lot more when we get to some of the strategy lectures. But for now, just be aware that the complex environments, extrinsically complex environments, tend to exhibit behaviors that appear orderly for a while, but then exhibit sudden shifts. One particular phenomenon that is very commonly observed within landscapes that are extrinsically complex is the presence of power laws. For example, if you look at price shifts, what happens is, for a lot of the shifts tend to appear fairly random, but every once in a while you'll get a shift that is dramatically outside of what you'd expect from a normal random distribution, which is known as the Gaussian. And what this means is that when you are designing systems that are going to operate in a rugged landscape, you have to be aware that there will from time to time be these long tail events. There's a book by Nassim Taleb called The Black Swan, and basically the central theme of this book is that when all you've ever seen is white swans, you have no way of knowing whether or not a black swan exists. And a black swan event is one that dramatically changes the system you're dealing with. There are also what he calls gray swans, and these gray swans are these power law events that fall outside of the normal range that you would expect. And a lot of financial models have failed because they did not detect or predict black swan events. Indeed, as I broadcast this lecture, we're living through one right now, the coronavirus, which has had a huge impact on the stock market, one that falls way outside what has been observed in the past, or what our financial models would cause us to expect. One of the challenges that we often face is can we counter these power laws? And it is possible to clamp down on a system, which is indeed one of the things we're trying to do with the coronavirus, but it is very difficult and it often has unintended consequences. Since I'll be referring to the term quite a bit in future lectures, I'd like to take a quick sidebar here and talk about what I mean by a power law. And a power law is essentially a relationship which appears as a straight line on a log-log graph. And typically, one axis will be the logarithm of the frequency of the event, and the other will be a logarithm of the size of the event. As I mentioned a few slides ago, when you've got power law relationships, long tails have a significant impact beyond what you would expect. Now, what do I mean by a long tail? Well, in statistics, there's a theorem called the central limit theorem, which basically says if you get enough random variables and add them together, ultimately you're going to end up with a normal distribution, otherwise known as a Gaussian distribution. Now, one of the things about the Gaussian distribution is it has a predictable behavior as you move away from the mean. So basically, 2/3 of your observations will occur within one standard deviation of the mean. 95% of your observations will appear within 2 standard deviations of the mean. And once you get to like 5 standard deviations away from the mean, virtually no observations are ever encountered because it falls off so steeply. When we're dealing with long tails, what happens is it looks a little bit like a normal distribution for the most common events, but when you get 5 or 6 or 7 standard deviations away from the mean, you still will get occasional observations. And those observations can have a very big impact. A good example of something that exhibits this type of behavior is earthquakes. So if earthquakes were distributed according to a normal distribution, then what we would discover is you'd never have a very big earthquake. Whereas if you're distributed according to a power law distribution, from time to time you will get an earthquake that is very, very big. It won't happen very often because logarithms fall off pretty quickly, just the way normal distributions do. But it will happen occasionally, and it's something that you have to think about if you're planning on operating in the system for a very long time. So it turns out that nature is pretty complex, and so are human systems, and as a consequence, power laws crop up all over the place. I've already talked about the fact that the magnitude of earthquakes is distributed according to power laws. What are some other examples of power laws that we see? Well, the size of cities is distributed according to power laws. That was one of the first observations that led to the 80-20 rule by Pareto, and I'll talk about that a little bit later. The distribution of citations to papers. if you're a researcher. There are some papers that just get an extraordinarily large number of citations. Price changes in cotton. I think this was originally known as Zipf's law, but it turns out to be a power law. The volatility of commodity prices every once in a while will show a huge spike way outside the sort of standard deviation that you'd expect from a normal distribution. The size of companies is distributed according to power laws. Income and wealth tend to be distributed according to power laws, which produces huge inequalities as a consequence of the fact that these power law distributions have very long tails. Asteroids have a distribution of size according to power laws, which means that there are some really big ones. And there are many, many more examples of this. But the point is, when you're operating in complex environments, you need to be aware that standard statistical techniques and assumptions like normality may not apply in some cases, and you've always got to be attuned to these power law potential distributions. Now, I just mentioned the 80-20 rule, and that's something that business people are frequently taught. 80% of the work gets done by 20% of the people. 80% of your problems come from 20% of the people. All these types of pithy rules. But the actual 80-20 rule is a power law. And one of the things about power laws is they're sometimes referred to as scale-free distributions, which means if you stop at any point in the power law and look to the end, you're going to see the same overall distribution. So if income or wealth is distributed according to a power law, and wealth tends to be, the top 20% of wealth will control 80% of the wealth. Okay, that's unequal, but it doesn't sound that disastrous. But if you look within the top 20 and multiply it by 20%, the top 4% is going to have 80% of the 80, or 64% of the wealth. The top 0.8%, again, just doing the same multiplication, has 51% of the wealth. So the top 1% is going to have more than half the wealth, which is actually true across the globe. The top 0.16% has 41% of the wealth. The top 0.032% has 33% of the wealth. The top 0.006% has 26% of the wealth. So you actually have huge inequality associated with the 80-20 rule. But just remember, complex systems tend to generate power laws, and it is very, very hard to interrupt that process. And usually when you do, you end up with unintended consequences. So let's summarize some of the impacts of environments of high extrinsic complexity or growing extrinsic complexity. One of the phenomena that you're going to encounter is localization. There really aren't any general rules. There are lots of rules that may apply to a local peak, but just like the question of should we add garlic to this recipe, if you're seeking another peak, you may have an entirely different situation. Because of this localization, we often tend to imitate others. If we can get a group together of people who are very self-similar, who have very similar interests to us, then in a sense we can watch each of those individuals do experiments, i.e., try a new clothing style or something like that, and we can see the fitness before deciding whether to do it ourselves. Because remember, in these high extrinsic complexity environments, very small changes can have a large impact. So in many cases, we don't want to necessarily do the change ourselves. So I've done some simulation where I really looked at this, and one of the things that I found is that imitation tends to be a very good strategy. And we'll talk about that a lot more as we talk about how technology is impacting our decision making. Combinations determine fitness. Causality really isn't that meaningful. It may be useful in a sort of an underlying way to try to understand the theory, but when an environment is very complex, you really have to experiment to determine what fitness is going to be for a given combination. You will not necessarily be able to come up with a theory. And I mention these things because a lot of what we do in an MBA program tends to be giving you rules of thumb to look at, giving you theories. And you have to realize that in a high extrinsic complexity environment, these are not necessarily going to work very well for you, and you shouldn't be too confident about them. Now, another thing is we're going to tend to cling to peaks because it's very, very risky in a highly complex environment to move off a peak because the drop-offs can be very, very sharp. Now, what that means is that when we finally decide to move from peaks to peak, we're going to tend to try to move very, very quickly. And this means that transitions can occur very quickly, which may be part of the explanation for the punctuated equilibrium behavior that you so commonly observe in these systems. And what that also produces is things called information cascades, where essentially you judge your actions based on the actions you're seeing others do. And if everybody's doing that, what will happen is as soon as one person does an action that appears to increase fitness, a lot of people will imitate it. This, by the way, is also a model that can be used to describe the spread of diseases. Finally, we need to expect power laws will frequently appear, and we need to plan for them. If you don't plan for power law events, then you can be very successful in the short term, but in the long term, you will invariably end up losing everything. So before I wrap things up, the final topic I want to introduce is that of efficiency versus adaptable, which I think is one of the most important trade-offs that you need to make when dealing with complex environments. So, looking at it from a complexity standpoint, being efficient involves being able to achieve goals with the minimum amount of resources, maximizing productivity, typically in routine situations. And being highly efficient is great for intrinsic complexity. That's what we strive for when we're dealing with intrinsic complexity. And it works very well during those periods of equilibrium between punctuation within complex systems. So as long as the system is not terribly extrinsically complex, and you can expect long periods of orderly behavior, then being efficient and tuning to those behaviors is going to be a very effective strategy for making profits and succeeding. Now, being adaptable involves the ability to change goals and change behaviors with a minimum amount of disruption. Being adaptable allows for survival in the event you have something large and unexpected occurring, but it's costly. And so being highly adaptable is a great tool for dealing with high levels of extrinsic complexity, but it is going to involve a number of costs. And we'll give some examples of these in later lectures. The key thing to remember is, depending upon the type of complexity you're dealing with, if it's intrinsic complexity, worry about efficiency. If it is extrinsic complexity, you gotta make sure you build in adaptability. So it's time to wrap this lecture up with a sort of brief summary of some of the implications that come out of the discussions of complexity that I presented here. As we think about complexity, and this is sort of a preview of lecture number 3 in the series, let's think about what is happening as the world economy is changing. one of the things that we're seeing is the number of participants in our system is growing. One of the major impact of globalizations is that all of a sudden now many different countries and groups of people are involved in the production of even simple items. The level of interrelationship between these elements is increasing as well. It has become much easier to communicate quickly across boundaries, to involve more people in our decision making, to have greater interrelationships. Formerly independent systems are now colliding. So suddenly the United States is being heavily affected by a disease that originated in a wet wild animal market in China. And these impacts allow for potentially greater disruptions in this system, which exhibits punctuated equilibrium behavior. Finally, the speed of communication is growing and shortening the timeline between events. So as events that might have taken centuries to occur and be transmitted across the globe in earlier, simpler times, when the fastest means of communication was riding out on horseback, what we're now seeing is a compression of the timeline, and phenomena can move across the system directly more rapidly. The bottom line is the world is becoming more extrinsically complex, and one of the focal points of this lecture series is what the implications for us are as decision makers and as individuals and organizations interacting with this system. So if you've gotten this far, I want to thank you very much for watching the slides. And if you have any questions, do not hesitate to email me at my email address, which is Grandon, that's Grandon, at usf.edu. Again, Grandon, Grandon, at usf.edu. Thanks again.